Hello friends, welcome to another lecture. Today we are going to discuss the properties of particulate masses, the properties of solid particles, in other words. Okay, so why we need to study this? Because, okay, first we will take the case of fluids. Okay, so fluids, we can have liquids and gases, right? So you already know Pascal's law. If I apply a pressure here, then it will be equal, and it will be right angle in all directions, right? If I apply pressure here, then this pressure will be transmitted same in all directions. Okay, in case of liquids and gases, that is your Pascal's law, right? But instead of liquids and gases, if you use solids and you start applying pressure in one direction, suppose you apply pressure here, this is a solid mass, right? Then what will happen? The pressure will definitely be spread in all directions, but this pressure will not be equal to this, right? This pressure, this is the applied pressure, and this is the transmitted pressure in this direction at 90 degree to this applied pressure. So this and this P and P dash will not be same. In fact, the transmitted pressure will be less than the applied pressure. Okay, so now why this is happening? Because these solids have distinct properties than liquids and gases. What are those properties? Okay, we'll see. Let's delete this. Okay, so we have different properties for solids, as is mentioned here. So the pressure is not same in all directions, as I told you. Okay, if I apply pressure to a solid, then it will not be same in all directions as the applied pressure. Okay, and it is the minimum in 90 degree direction. So this is 90 degree, right? So this is 90 degree. So in this direction, it will be the minimum pressure felt if you apply pressure in this direction, right? But for liquids and gases, it is same in all directions. Fine. Second, a shear stress applied at the surface of mass is transmitted through a static mass unless failure occurs. Okay, if you suppose there is a heap of solid particles, let's say you have a sand heap of sand, then if you apply shear stress, right? You know shear stress. So you know normal stress. So normal stress is like, suppose you have an area here. This is the area, right? If you apply at a 90 degree to the surface, that is your normal pressure. Okay, what is shear stress? Or this is normal stress. What is shear stress? Suppose you have this volume, surface, this is a surface, you're applying on this surface, but not in at a 90 degree to the surface, but parallel to the surface. If you apply in this direction over this surface, right, then this thing will be moving in this direction, right? This is called shear stress. So if you apply shear stress to the, let's say, heap of a sand, then what will happen? This will try to move in this direction, right? And this force will be transmitted in this along this also. So this heap will try to move in this direction. Okay, what it is saying is it will move, right, as long as you apply shear stress in direction, but at certain time what will happen? This will break off, direct break off. It will look something like this. It will just break off. Okay, because when you apply shear stress, the particles interlock with each other, right? So if the failure occurs here, then it will just break off. Okay, that's what he's saying in this point. Okay, third point, we have the density of mass may vary depending on the degree of packing of the grains. Okay, so what it's talking about the density of the solids. So what it's saying is, so suppose you have a particle, right? So the density of this particle rho p and this particle rho p will be same because these are made of same material, right? But this is individual density, okay, individual particle. But what about the bulk density? Bulk density in the sense, suppose you have a mixture of particles of same diameter, right? So if you take as such, see the density will be a function of the void fraction or how tightly or loosely packed. If it is loose, the density will be different. If it is tight packing, then it will be the density will vary, right? Suppose you have this container and you have loosely packed solid particles, then the density will be something. And if you have very densely packed, right, all are filled, there is very less gap in between the particles, then the density will be very high, right? So the density of the solids will vary on the degree of packing, how much void fraction is there, okay? But in for air and liquids, the density almost remains constant, right? It doesn't depend upon the degree of packing. Fine. Okay, this is done. The number point 4. So it says before a mass of tightly packed particles can flow, it must increase in volume to permit interlocking grains. What it means is, suppose we have solid particles, okay, packed solid particles. See, if it is tightly packed, it is very tightly packed, okay, then what will happen if you just try to pour this, right, will it flow? Yeah, definitely will flow. But if it is very tightly packed, it will not flow as a fluid, it will directly drop off, right? The whole thing will drop, okay. But if it is loosely packed, then what will happen? And it will flow like fluid, right? Let's say you are trying to pour 1 glass of rice, right? So you have a glass, there rice is there. If you try to pour it, it will uh, like try to flow like a liquid, right? But instead of rice, if you take atta, it will not flow like this. It will be the flow will not be similar to the liquid. It will like flow like chunks of, right, chunks of atta, okay, because the if in the case of rice, the interlocking between the particles was not much, right? But in case of atta, the atta particles will be interlocked with each other, so they will not they will be reluctant, they will not flow, okay, like liquid. So so if solid particles wants to flow, then it will depend upon its interlocking particles tendency. So it basically depends upon the type of solids, okay. So you might ask why we are studying this, because in chemical engineering you have to transport solids, right? Suppose you have a sugar factory and you want to store the sugar, right? And you want to transport the sugar. So during the transportation process, this industry doesn't employ batch operation, they employ continuous operation. Whatever you do, it should be continuous, right? So it will be very difficult to transport solid particles like sugar crystals, right? So to make it easier, we have to know the properties. That's why we're studying this. Fine. So based on these properties, you can classify solids into two types. One is cohesive and another is non-cohesive. Fine. What do you mean by cohesive? Cohesive, the example is clay. You can say atta or maida. Okay, and cement. You can say cement. And in case of non-cohesive, you can say sand, gravel, rice. Okay. So if you have observed from daily observations, you can say that it is if you want to pour rice from a bin or bucket, it is very easy, right? The rice will flow very smoothly. But if you want to make atta flow, it's very difficult. And if you want to pour clay or cement from a bag, it is very difficult. It will not flow exactly like liquid. Okay. So based on this, it is defined. So we have two types of solids, cohesive and non-cohesive, and examples are this. Okay. Now next, let's study if I apply a pressure, then what will be its pressure value at 90 degrees or at any angle theta. Okay. In case of liquids, I already told you, in case of liquids and gases, if you apply a pressure P, then it will be same at right angles, right, in all directions. But in case of solids, it's different. In fact, it's less than the applied pressure. Okay, so let's see that. Okay, so we have a masses of particles here. So let's say masses. Suppose this is a bulks particle. So if I apply a pressure P, from now on I will say PV. PV means applied pressure. Okay, I'm applying some pressure. Okay, and I will say, I told you, right, the pressure will be different in all directions and it will be minimum in this 90-degree direction, right? So I will say this minimum pressure as PL, right? If you apply a pressure PV to the solids particles, then the pressure transmitted at 90 degree will be the minimum pressure, and this will be denoted by PL. Okay, just notation so that we can do some derivations. Okay, I will define another term called K dash. This is the ratio of this normal pressure. This is also called normal pressure. The minimum pressure at 90 degree to the applied pressure, that is normal pressure. Okay, so PL is normal pressure. So if you take the ratio of PL and the applied pressure, that is normal pressure and the applied pressure. Applied you can apply with hand or some machine. Okay, it's a different thing. So normal pressure divided by applied pressure is defined as K dash. It's a constant. Okay, so if you ask me what is the K dash for sand, clay and atta, all will be different for these three materials. Okay, so all these materials have different properties, so the K dash will vary. The K dash of sand, clay and atta will be all different. Fine. So K dash is a function of only the material. Okay? It is not a function of size. Okay. So see, if I take a sand of dp diameter 1, dp1, and if I take a sand particle of dp2, okay, the k dash will remain constant for both the sizes. Okay, because k dash does not depend upon the size of the party or grains. Fine. K dash basically depends upon the interlocking tendency of the solid particles. As you can see, the interlocking tendency of atta will be higher, and for clay will be higher, and for interlocking tendency of the sand will be less. Okay. Now let's derive a formula so that I can calculate the pressure at any angle to the applied pressure. Okay. Suppose I take a solid here. A solid is the mass of solid. Okay, solid here. If I take a small section of here, let's say it is like this. I have taken small section of this. This is in 3D. Okay, this is in 3D. So this small section will also be in 3D. So if I apply a pressure, let's say in this direction, V applied pressure. So the minimum pressure will be in 90 degree directions, right? PL. What if I apply pressure to the solid at an angle? I want to apply this pressure at an angle. It's not, let's say, this was 90 degree, right? So if I apply PV, then it will be this. But I want to apply the pressure at an angle. What will be this PL or the pressure here, P? Right? PL is the minimum pressure, or it is called normal pressure because it is 90 degree. This will always be at 90 degree to this. Right? If I apply the applied pressure at an angle, then at 90 degree it will be PL, it will be always minimum. But what about the uh, pressure in any direction, here? So let's find out by deriving a formula. Okay, so okay, so I will draw a sketch. Okay. Okay, here it is drawn, right? A triangle, a hypotenuse, right angle triangle. Okay, so I have rotated the simple square at a certain angle. Okay, then taken the half of that square. So you can see here. Okay, okay, fine. So I have this triangle. Let's say the applied pressure is in this direction. Okay, this is your applied pressure PV. Okay. And at 90 degree to this PV, this is your 90 degree direction, right? So you will be having a PL, that is the minimum pressure. Okay, let's say the hypotenuse is of length DL because we are taking a small element, so we are saying DL. Okay, so what will happen if you apply pressure at 90 degree? There will be no shear stress. Okay, but if you apply pressure at an angle, then there will be shear stress as well. So here you can see the shear stress will be in this direction. Okay, tau is shear stress, and this is the pressure. I want to calculate the pressure in any direction, right? So I want to calculate the pressure at P. Okay, at any angle. So it will be a function of this angle. Okay, so we'll derive it. So let me erase this. Okay, so if this is the PV, then what is this length? Definitely this is the hypotenuse, right? L. So you have hypotenuse theta. This is some, if it is DL, Then what is this? dl cos theta, right? And this is dl sin theta. So this length is dl cos theta, and this length is dl sin theta. Okay, fine. What will be the area? See, this is the side view. Okay, this triangle we have taken is a side view. Actually, it is if you see it, this is nothing but kind of 3D, right? So we are taking this side view. And what is this thickness of that triangle? This is taken as B. Okay, this is B. So what is this area? What is this area? Sorry, not this one. This one, the bottom one. What is the What is this area? This will be basically this length into B, right? So this length was what? dl cos theta, dl cos theta, and what is the thickness? That is B. So area will be B dl cos theta. Okay. Similarly, the area of this face will be not this one. The opposite side. This one will be your this length into thickness, right? So that is B dl sin theta. Okay. What about this area? This area will be your B dl, right? This is B and this length is dl. So length into break B dl. Okay. So so now I will resolve this PV into different components. Okay. So this is at theta, right? So this was the direction of your PV. Okay. So what is the angle here? Sorry, let me change the settings. Need to check. Now this. Okay, so you have this PV in this direction, applied pressure. Then if you draw a parallel line to this, so this will be theta, right? And this is resolve this PV into its components. Okay. So PV cos theta, right? In this direction, parallel to this hypotenuse. So in this direction, which is parallel to the hypotenuse, if you resolve PV, then in this direction, what is this? PV cos theta, right? And at 90 degree to the hypotenuse, what it will be? PV sin theta, right? Right. And what will be, if this is the pressure, what is the force? You have pressure. What is the formula of pressure? Force per unit area. You want to calculate the force, so force is equal to pressure into area. If this is your pressure, right, what will be force? So into area. What is the area of this cross section? That is dl cos theta, right? B dl cos theta. Similarly, what about this? Again, same. You just have to multiply with B dl cos theta. Okay. So cos theta sin theta. So you can see here, this is the component of force in this direction along the hypotenuse. This is the component of this force in this direction, that is 90 degree to the hypotenuse, right? Cos square theta, because this cos theta will become square cos. Similarly, you can do here, right? You can resolve this along. So okay, I will show you. Okay, so the PL was in this direction, right? Now draw a parallel line. something like this. So what will be this angle? So it will be better if you take here. So take here, this goes this is goes this here. So this corresponding angles, this will be theta, right? This will be theta. Okay. So this no, no, this is your 90-degree direction. The pressure is not in this direction. Pressure is in this direction actually. Okay. So if this is theta, then you have the cos theta will be there. B dl. Yes. So this is your minimum pressure, and this is a theta, right? And this is your direction to the perpendicular to the hypotenuse. Your minimum pressure is in the direction theta, and along this it will be this. So this is your PL. So PL cos theta, this will be PL cos theta, and this direction it will be PL sin theta, right? So what about force? So just multiply with this area of this cross section, and area of cross section was BDL sin theta, right? Okay, into just BDL sin theta. So it becomes sin square theta. Okay, you can do it. This I think there is some confusion here. BDL sin theta. This was already and cos theta. I think the angle will be this will be I think 90 minus theta. Oh yeah. So the rest will follow the same. Okay, so cos 90 minus theta will be sin theta, and this will be cos theta. So you can get other components as well. Okay, now let's make a force balance. Okay, if you do a force balance, so I will make a force balance in two directions. Okay, so direction one in this direction and one in this direction. Okay, this is along the hypotenuse, and this is perpendicular to the hypotenuse. Okay, so first I will take the this one perpendicular to the hypotenuse. So we have this force, this one, right? And in this direction we have this one opposite to that, and yeah, this one, right? This is also in design. So this is equal to this plus this. Okay, so you can see here, so PBDL is equal to this. Okay, so we have got first equation, right? Similarly, just divide by BDL on the both sides, and you can simplify it to this. Okay, similarly, I want to find shear stress, then just do the balance in this parallel to the hypotenuse direction. So what are the forces here? So in this direction we have this tau BDL, that is force only, and it is this one is there, PVDL cos theta sin theta, and this one is there, right, in this direction. So you have what, tau BDL, this plus this equal to this, because this is opposite, right? So if you do and simplify, divide by BDL only, you will get tau. Okay, there's PV minus. Okay. Fine. Now you have got this as well, right? Now I want to plot this on graph. Okay. So what I will take is I will vary the theta from 0 to whatever value, 180 or 360 degrees. and plot all the values on the graph, then you will see that you'll get a circle. Okay, so that is called more stress circle. Okay, I think to move here, yeah, you will get this circle. Okay, you will get this circle. You are plotting between the pressure calculated and shear stress, right? On x-axis you have the pressure P, and here see you are applying pressure PV, right? And you're getting minimum pressure normal to the PV, that is PL, and at any angle theta there will be some pressure and shear stress, right? Okay, so that any pressure at any angle theta you'll get this, so you'll get a circle here. Okay, now I want to find some angle. Okay, if you this thing and the angle between this alpha, this is called alpha, right? So if you find the angle, you make it. So this is the more stress circle, more stress circle. This is, you might have studied this in engineering mechanics. Okay, fine. This more stress circle has a center at, the center point is equal to, let's see. Okay, so the center is at P is equal to PB plus PL by 2, and the radius of that circle is PB minus PL by 2. Fine. So if you see this graph, the alpha is nothing but what? This, if you see, this is a right angle triangle, right? This is your right angle triangle. So how you calculate alpha? That is nothing but tan theta, right? Or you can say in terms of alpha also, sine also. Yeah, sine will be, so this is your hypotenuse. No, this one is your hypotenuse. Or this one is, yeah, this one is hypotenuse. And this is your perpendicular, and this one is your base, right? So what is sine? Perpendicular by hypotenuse, right? So sine alpha will give you, because the main aim is to find alpha in terms of the PV and L. So this you will get. So what is the radius? So you will get sine alpha is equal to PV minus PL, I think, by 2 is missing here, and PV plus PL by 2. So 2 cancels out, you'll get this formula. So sine alpha is equal to PV minus PL by PV plus PL. Okay. What is alpha now? Well, alpha is, look at, so alpha is called angle of internal friction. Fine. So you always know what is angle of friction, right? So this angle of internal friction is the angle between the solid particles. Okay, angle of friction between the solid particles. Okay, so you can find out the angle of internal friction. Now next, you can express this angle of internal friction in terms of k dash. You know, k dash is function of particular material, right? So you have sine alpha m is equal to angle of internal friction PV minus PL. This should be 2 here, this machine. So PV plus PL, right? Now divide, you know, k dash is equal to normal pressure by applied pressure, right? So just divide numerator and denominator by PV. So you'll get 1 minus PL by PV. Similarly, 1 plus PL by PV. Just replace PL by PV with K dash. So you'll get this formula. Now you can rearrange this equation to get K dash in terms of sin alpha. So this, if you rearrange this, you'll get this. Now you can see K dash can be calculated using internal friction. Okay. Now there is one more term called angle of repose. So what is angle of repose? Suppose you pour a sand on some surface, so the sand will get collected like this, right, as a heap, a conical heap. So this angle theta or whatever is there, so alpha m was angle of internal friction. So I will, here it is denoted as alpha r. That's the angle of repose. Okay, this is called angle of repose. If you pour solids on the surface, it will make a heap in the form of 3D cone. Yeah, cone is 3D. It's a cone. So the theta, the angle with the slanting side will make with the surface. That is called angle of repose. Right? Fine. So it is also saying that if the the solids are homogeneous, then angle of repose will be equal to angle of internal friction. Okay, but in general, the angle of repose is less than angle of internal friction. Okay, next, okay, so there's a range of K dash values given. So it is saying K dash approaches 0 for a cohesive solid. Cohesive solid means very highly sticky, right? If you uh, make a heap of solid for a cohesive, then it will be as straight as this. So the angle of internal friction will be around 90°. So if you put 90° as the angle of internal friction in this formula, sin 90 is what? 1, right? 1 minus 1 is 0, and here 1 plus 1 will be 2. So 0 by 2 is 0. So K dash is 0. So for very cohesive solids, K dash approaches 0. Right? It approaches 0 for a very cohesive solid. And in general, if it is not highly cohesive and it is also not very non-cohesive, the value will lie between 0 and 1. Right? So the generally free-flowing granular materials are the K dash value is between 0.35 and 0.6. That means alpha angle of internal friction will be equal to, the range is from 15 to 30. How? Just use that formula. You know the range of K dash values, right? The K dash range is from 0.35 to something, 0.6. So if you put 0.35, then calculate alpha m, you'll get the alpha value as 15°. And if you put 0.6 K dash, then you solve it for alpha, you'll get the 30 degrees, right? So we have also found the range. Okay, next, so how to store the solids. Okay, so you can store the solid as a bulk storage. Bulk storage means just dump it. Okay, dump it in the open. Have you seen the storage of coal? So for near the railway tracks, it's just dumped on the open, right? The coal is just dumped in the open as heaps, right? So that is your bulk storage. See, you cannot store Suppose you want to store salt or some chemical, powder chemical, in the open, right? Because this all will dissolve with water. But in case of coal, it is possible, right? There is not much loss. There is not a very, runoff. Okay, so if you store the coal in the open as a bulk, there will be no runoff, or there are not much loss. Only you have to close with certain cloth or some plastic, right, covering. But in case of solid chemical, you cannot store in open, right? So bulk storage is not possible. Also, bulk storage is for those where the it's very huge. Like coals are produced in tons, right? You cannot store tons of coal inside some bins or tanks, right? So it is stored in bulk storage in the open, right? But if you want to store salt or some valuable chemicals, then you have to use bin storage. Okay, what is bin storage? So what beans look like? Like beans is like something like this, very short and cylindrical kind of thing, right? Cylindrical storage tank. Okay, and you can have hoppers, this conical kind of thing, or kind of bucket also, let's say. So these are called bins. And there's one more thing, silos. Silos are like tall cylindrical storage vessels with very small diameter. Okay, they are silos. So you can store in bins and silos. Okay, if it is very valuable material, you have to store in these bins. Fine. So there are some. What happens if you store solids in bins and silos? What will be the pressure? So you can see what is the criteria. You can read about it on this side. So now you have stored the solid inside a bin, right? Suppose you want to take out the solid. How will you mm, take out the solid? Definitely there is some opening at the bottom, right? So you can take out from this bin from the bottom opening. Okay, sometimes what happens while uh, trying to take out the solid from the bin, what happens is like the solid stick on the wall, and only the center, the solid at the center to this axis will flow out. Okay, leaving only tunnel here. So that is also something called tunnel flow. Okay, so there is one expression, right? If there is an opening at the bottom of the bin, okay, so the flow rate, how much solids will flow per unit time, will be function of this opening diameter. Okay, so it is something like this. So flow rate m dot will be the units will be kg per hour or tons per hour or gram per second, whatever you prefer. So it is a directly proportional varies with like the power n. Now n, the value of n is about 2.8 for angular particles. Angular particles in the sense some particles have some irregular particles, right? And it is about 3.1 for spherical particles. Okay. Also, you have conveyors. So we'll study this in detail later. Okay, we say conveyors means conveying. What do you mean by conveying? Conveying is transport of materials from one place to another, right? Okay, so there are different ways to transport. We have belt conveyors. So you have a belt, right? This belt moves and the solids are put. So the belt is moving. There is some motor is here, so it will rotate. So this solid can be moved from here to here over long places. Okay, even with bucket elevators. Bucket elevators is something like you have bucket, right? You want to transport from the solid pour in the bucket. So using elevator, it was transported up, right? During construction work, like yeah, there are examples. Fine. With this is the end of the chapter one. Okay, we'll solve some numericals if possible in the next class. Okay, thank you.